Hello fellow designers, today I'm going to introduce you to Grasshopper, a powerful visual programming tool integrated with Rhinoceros 3D, revolutionize the way architects and engineers approach design by enabling users to create algorithms using a node-based editor. Grasshopper transforms complex geometrical modeling into an intuitive and interactive experience. This innovative tool empowers professionals to explore new dimensions of creativity and precision in their projects, pushing the boundaries of what is possible in architecture and engineering. Grasshopper's strength lies in its ability to seamlessly integrate algorithmic thinking into the design process. Unlike traditional CAD software, which relies on manual drawing and modification, Grasshopper allows users to define parametric relationships between elements. This means that changes to one part of a design automatically propagate throughout the entire model, ensuring consistency and efficiency. By using algorithms to generate forms and structures, designers can easily iterate and explore a vast array of possibilities, leading to more innovative and optimized solutions. Algorithms serve as the backbone of modern engineering, transforming how we conceive, develop, and execute designs. In the context of Grasshopper, algorithms enable the automation of repetitive tasks, the optimization of structures for performance and sustainability, and the exploration of complex geometries that would be infeasible to model by hand. For instance, algorithms can be used to generate organic freeform structures that mimic natural processes, resulting in buildings that are both aesthetically pleasing and functionally superior. The integration of algorithms into design and construction is a paradigm shift, fostering a more dynamic and responsive approach to problem solving. By leveraging the computational power of Grasshopper, architects and engineers can create adaptive systems that respond to environmental conditions, user needs, and material constraints. This shift from static to dynamic design thinking encourages a holistic perspective where every aspect of a project is interconnected and optimized. Moreover, the use of algorithms promotes collaboration across disciplines. Engineers, architects, and fabricators can grow together more seamlessly as Grasshopper provides a common platform for developing and testing ideas. This collaborative approach leads to more innovative and sustainable solutions, ultimately transforming the built environment. In conclusion, Grasshopper is not just a tool, but a catalyst for innovation in architecture and engineering. By harnessing the power of algorithms, it redefines the design process, making it more efficient, creative, and responsive. As we continue to embrace these technologies, the potential of groundbreaking advancements in design and construction is limitless, promising a future where our built environment is more harmonious, functional, and inspired by the complexities of nature. Hello designers, welcome to our new episode on Nonconventional Design. I'm Ghaith, and today I will lead you through our video tutorial on using Grasshopper. This video meant for people who wants to learn new skill in Grasshopper. As you see, this is Grasshopper interface. You could add like color schemes in the beginning, and then this is the component folder where you could add like plugins. For example, Millipede, and you see it up on the tabs. on the tab, on the plugin tab. Now let's start. You could also like put some notes. It's pretty cool tools up there. You could check it out yourself. Make sure that you check this green button up above, and let's delve into our tutorial. So that's a basic script in Grasshopper. This is a point. This is a plane. You see the point has a X, Y, Z coordinates. This is a plane where you could place objects and locate them. This is a circle program, and this is an output, which is a circle curve basically. And this is a radius of the circle. We could always adjust it what we want. These are parameters types. So this is a parameter of type circle. This is a parameter of type curve. To people who knows programming, see that the type, for example, here in Grasshopper get changed automatically, get converted automatically. Even like the circle is not an integer, but even though it receives a value in the integer variable. So that's a basic Grasshopper script. So now we'll delve into list operations. I will just gonna create a very primitive list. So these are two lists of 2 points. These are 2 lists of points. And now we're gonna apply list commands on them. So first I'm gonna connect them using lines. So list 1 get connected to list 2. This is cross reference. It means each point is gonna connect it to all points of the other list. This is a long list. So if a list is smaller than the other one, the last element is gonna get copied and the first list is gonna connect to it. And this is a short list where the first list get connected to the same number of points of the other list. This is a weave where we put a weave pattern and we weave between 2 lists. So you see that the curve is jumping from points from one list to another point from another list, and you create this zigzag. This is a helpful tool to show you the order of the points in the list. So now we are gonna get you introduced to range, how to create like a range of numbers, and we're gonna use that as an input for an x coordinate of points. And you see like we could adjust how many steps are there inside the range, and the points, we get more points. And here is the series, where the series we don't have a like fixed domain, but we could always like add steps and counts. The step size could be adjusted, and the counts is basically what makes the list grows. Now we're gonna introduce you to shift list. So basically shift list is to shift the order of the numbers inside the list, of the elements inside the list. So now I shift them by 11, but you're gonna now see the changes when I shift. You see that the 10 is coming down because it's shifted by 6 basically, and so forth. And you see the connections, how they get changed because each point connected to the point with the same order. And if the order gets changed, then the connection's gonna get moved. And now I'm gonna introduce you to dispatch. So through this conditional, I'm gonna split a list into two lists according to their x coordinates, if it's larger or smaller than a specific number. As you see, so A is basically the one gets picked out and B is the one get neglected according to the conditional. And now I'm gonna introduce you to data trees. So data trees is the way that data is structured in Grasshopper. So I'm gonna create like a 2D grid of points using graph, and then I will use the graph again to move this grid on the z-axis to create copies on the z-axis. And I'm gonna retrieve the tree structure. Now I'm gonna pick the branch after retrieving the tree structure of one level, so to say, and then I'm gonna retrieve the row, basically the rows of this level. I'll flip the matrix, so I flip the rows and columns. I'm gonna check them out, and you see now I can pick the column now. By the way, this only works if the list and the number of paths of the tree matches. If they don't match, I mean, the matrix won't get flipped. So this is basically the structure of the data and how we could always keep control on that structure to retrieve information. In this case, there are points. And now we're gonna try to do the same thing by creating segment surfaces using segments of the curve. So now I'm gonna create two lists where I delete the first and the last item of each one, and then I will merge them out so the rows, so the first row and from the first one matches the first row and the second one, and then I will create lofts of the segments. And now I could always, by shifting paths, I could always retrieve the row basically of the segment surface. And if I flip it, I get the column. So that's also one way of seeing data trees, basically. These are now vector operations. So if you know the vector from school, time, it has an x, y, z. It's basically defining a direction. We could bring it from there, from the math, from the vector tab, and we could visualize it as well by the display vector. This is a sum of two vectors. This is one vector. This is a unit vector where x get changed. This is summation. So this is a vector, this is the x basically. This is a vector growing on the x. This vector is growing on the x plus epsilon, or x plus y. Vector growing on the y. This is a summation where the x get changed and the y get changed. Now I'm gonna introduce you to cross product, which is a vector that is perpendicular to the plane where two vectors are, basically two inputs vectors are. So now we add two vectors a and b, and we get the one which is perpendicular to both of them together. So see vector b, and this is the dot product, as you see. Two vectors always form one plane. That's from the math school. Now we move to dot product. Dot product help us to, which is the trajectory of one vector over the other one, and it helps us to detect if two vectors have the same direction or not by dividing or by getting the sign of by getting if it's plus or minus. We know if two vectors have the same direction or they have like different direction. Different directions means that the angle is more than 90 degrees between both of them. I'm gonna produce the corrected vector, so to say, and now you see that it follows the same direction as we intended. It helps to maintain directions of like vectors resulted out of vectored operations. Now we're gonna check some conditional operations. So this conditional operation is basically checking if a number is larger or smaller, and then it gives you a boolean. If it's smaller, then it's if it fulfills this condition, then it's true. If it's not, then it's false. You see here on the larger than, and we also perform the same thing on the smaller than. Of course, more than or equal means the equal is also inside the condition. So if it's equal, it's gonna also get true as well. So now we're gonna move to the formulas in Grasshopper, which is if x, and this you could add to it to add formulas like in text in a text, and then you get a result if it fulfills it or not. You could also add like mathematical analytical formulas like this one, like summation of the squares of two numbers, and then you get numeric results. And you could also turn it into like geometric information, like here I'm gonna produce this helix-like geometry out of sine and cosine operations. I'm gonna use this if x to generate the coordinates, and I'm gonna link them through a spline. As you see, you keep the parametric control while the formulas like change the coordinates. And now we're gonna check the grapher mapper, which is another type of formula-like control. we have now, we're gonna test this sine formula on a range of numbers. So we get the epsilon or the y of this range x values, and we remap them. We'll remap the numbers so the values would be more than 1, because we wanna see them basically, just to exaggerate the values, so to say. And we see like it's a kind of way you parameterize coordinates. You could always check them out by interpolate them. Here you could play with a maximum value. To see them better, let's increase the number of points so the interpolation gets better. And you see the sign gets into shape, which is quite similar actually to the topology of the formula. Now we're gonna check the attractors. Now we're gonna build a grid of circles using their radiuses, and like I'm gonna move them according to the radiuses, but in a specific domain, predefined domain. So as you see, like they're touching they're all tangent to each other. And now I'm gonna use that to get some kind of response from a point, which I will call the attractor. And the attractor is basically a point that have a specific, now it's like a distance attractor, so basically it's a distance function, like it measures the distance between the attractor point and the centers of each one of these circles, and try to like make them smaller or larger according to how they are close or far from this point. And I'll make sure that they won't get messy and get intersected. Like, you'll check that out now. Let's check that out together. So now it's the opposite way around. So if it's closer, then the circle gets large, and if it's further, then it gets small. But that's not the effect I'm looking for. And now it's like it's getting into shape, but still have a problem that they get intersected because when the attractor is far away. And for that, I was just gonna make sure by remapping to limit the change in a specific domain, where the domain maximum value is basically the radius, the initial radius of the circle. And now I think it gets into like a better shape, and I get the response that I was looking for. See, attractor moving, circles getting smaller in specific areas and larger in other ones. It's a pretty cool effect. Could be used out to get some performance, bring some more sunshade, or like some static influence over a specific structure could be as well, etc. So see how distance get divided by the radius. And now we're gonna build a grid of boxes. We're gonna try to get this into these attractors to work on 3D. So we're gonna use now the X and the Z to build a 3D grid of boxes, and we're gonna make the boxes get the same effect as the circles in the first example. So you understand that this effect could be scaled to another dimension, so to say. So this is the attractor point. These are the grids. These are the boxes. And now moving the attractor basically. So you see, like, when they get smaller when they are closer, and they still being the same when they are further. But that's not the effect I'm looking for. So I'll remap them as I did in the previous example, and now we get the attraction. And here you see where it's maximum size. It's basically its origin size, and it gets smaller to the limits of the domain. And now we secure that the boxes won't go larger or smaller than we wanted. So let's color them out. So this is a gradient. We need the geometry, and we need the scales. Use the scale values to add them to the colors. I'm gonna switch things off so they don't disturb the view. Sorry. Give me a bit of time. Switch everything off. Now. So as you see, like, the furthest are the reddish boxes, and as they get smaller, they get into the green. So they correspond to the domain basically of the remapping. Here we could just grab this connection and go to, just to make sure, like, just to keep following the spaghetti. I'll play a little bit with the gradient of the colors and push the yellow closer to the limits, to the higher limits. Change the color code now. They're pretty cool gradients now. Now I'm gonna change the attractor position, and you'll see that the colors and the scales will get changed accordingly. Pretty cool rainbow. And now we are gonna delve into surface domains. So we've spoken about like domains so far. We use them to govern the lists of numbers, and now we're gonna use them to govern 2D domains on the surfaces, the UV domains. So I'm gonna build like fast the surface out of sweeps, of one sweep, by creating an arc and rotating it and sweeping it out. You make sure about the direction of the arcs, by the way, when you perform a sweep, because that might ruin the surface if the arcs don't, if the rails don't follow the same direction. As you see, like, get damaged. And now by flipping it using a guide, which is the other curve, now we maintain that the rails have the same direction. Pretty nice surface, shell-like surface, so to say. But the boundaries are not shell boundaries anyway, just for this example. This is where we bring the rotations, this is where we bring the flips, and this is where we bring the sweep. By the way, make sure to press Alt with Control and not only Control. Now this is the surface. I'm gonna divide it into points by specifying how many on the U and how many on the V. I'm gonna offset the surface. And now redivide the offset and connect them with lines. I'm gonna pipe the lines now. Pretty nice effect, like building filling structure for this shell-like surface. And now we're gonna create a circle grid again. A box grid. On 2D. And I'm gonna use this to morph geometry on the surface. So I can use first, well, I could use like different geometries, so to test like the morphing effect. But first I'm just gonna move the boxes. So I'm gonna divide the surface domain into a 2D domain, into UV domain. And I'm gonna use that to split the surface into subsurfaces. And these subsurfaces, I'm gonna use them out to build like the offsets, which will be used as morphed boxes by using the normals of the surface or the gradients, if you're familiar to differential geometry. So if we move the points, then we could like build the boxes, which they are twisted already, because the normals here, because the edges are twisted of the offsets basically. This is why we call them twisted boxes. Anyway, if they're not flat, they're gonna be twisted. That's the general geometry of the double curve, so to say, of the double curve segments. I want to show you the normals, how they look like, or the gradients. So these are the normals of the surface. These are the twisted boxes. Now we're gonna use the twisted boxes to morph the original boxes. So the original boxes will serve as a reference. I'm gonna use them as well as a geometry. I'm gonna morph them into the twisted boxes. So I will morph first the spheres. You see, like the sphere is distorted. It's not a good sphere. Like it's not a perfect sphere, which is something we don't appreciate much. So there is a trick, is like to pre-use the twisted boxes to generate spheres inside them with a fixed radius. And now I'm gonna show you how I'm gonna do that. So the sphere is not a good geometry to morph, basically, because it's gonna lose its spherical effect or geometry properties or features, so to say. And now I'm just gonna recreate this spheres to sit inside the boxes, and that's way better. Like, we preserve the geometry this way of the sphere. So the feature of the morph geometry is very important if we want to build like structures in the future. It's better not to distort it, because it's gonna be like, for example, if you're gonna use like material like wood or something, it's gonna have the same thickness always, like, and it's better for optimization, for production, and for other aspects of like keeping control of geometry, of like materials and manufacturability and assembly. But anyway, this is coming after this tutorial. This is not the subject of this tutorial. Now we're gonna try like to morph other geometry, which is gonna serve as a structure, as an inner structure again, and make sure to preserve its geometry. So we prepare first the guiding or the reference boxes, and then we're gonna use them to create the reference, the guide curves, basically. These are the guide curves, and it's better to morph the guide curves, the guidelines, because this won't change the features of the geometry. So the line is gonna stay the line after morphing. It's not gonna be a curve, or it's always gonna be a line. So it's a good geometry to be morphed. After preparing the data structure, and it has to be morphed, and now we're gonna morph these 6 lines, which are the inner lines that connects the faces of the box. So here we have the inner structure, and now we're gonna build the inner structure out of pipes, and you see like they're connected perfectly. And this is like a good example of like morphing structures by preserving geometric features. And now we're gonna like morph the panels. We could use also the panels of the like twisted boxes. And this is the structure we're looking for. I mean, this is not a structure, I mean, this is just an example. So there is no structural potential, but it's just to test the tools. It looks nice though. Let's switch this off. As you see, like, it's pretty good made morphing. But here I think we have problems. But I think we could just use the surfaces of the twisted boxes instead. Like here, there's on the bottom part there are some mismatching. But this we could solve it. Now we're gonna try to test gradient on the surface domains. So we create the surface again, and we try to play with the UV, and now I'm gonna play with the UV, with the U basically, and you will see that the sub segments we're gonna get shrinked on the U in some places and expanded on other places. So now we're gonna form this domain after changing the distribution of the segmentation. You'll see that they get compressed on the side. This is because of this grapher mapper. I'm gonna play with this a little bit to show you. the potential of the thing. And it's better not to move the sides because they define the domain of the surface. So only play with the handles, as you see, like these are the, and also play with the curvature on top of the and the bottom. More curved means more curved in the x, on the x size direction means smaller separations, smaller segments. This is how you could understand it. So now we made the small segments on the both ends. I'm just gonna bake them out, so you see the surfaces, the surface segments. Now I'm gonna do both on both sides, on the U and V as well. So the distribution is like variable on both sides, and you could see the results on the perpendicular ends. So this is the U and this is the V, and see how. And now I'm gonna make a symmetry kind of a thing on the U and on the V. I see the middle part has the largest panels now. Pretty cool control, right? You could find applications for it yourself, either from like adaptive structures, kind of freeform, or force-fitting kind of elements. Alright, I'll thank you now for watching my tutorial. I think we have a good hands-on work on using Grasshopper, the tools that I use to experiment with geometry and to experiment like with mathematical tools. In Grasshopper you could, as you see, like you could test any kind of mathematical or parametrical systems, and you could later on, or you could like put concepts of parametric systems. You could also put concepts of like geometry that has specific features while maintain the control, the parametric control, and you could always like test the features against specific thing like lightweight or force capacity.